Here's a summary of curve sketching that we looked at before. All the calculus-y stuff is over here, and all the algebra-like stuff that we learned in the past is over here, except for this limit as x approaches infinity. This is for horizontal asymptotes. This is more of a calculus thing. However, we did learn how to find horizontal asymptotes a different way back in Algebra 2. And that's actually the way I would prefer. But I will talk about x as x approaches infinity and why the limit as x approaches infinity actually does also give us the horizontal asymptote. Now, rational expressions is when you're going to need those horizontal and vertical asymptotes. Why? Because there's a condition here. We cannot have a zero in the bottom of a fraction. And so because we can't have a zero in the bottom of a fraction, that limits our domain. That gives us the vertical asymptotes. And then, just by the nature of a rational expression, we are going to have horizontal asymptotes. So to find the vertical asymptote, what you do is you take the denominator, you set it equal to 0, and so then we solve. Move the 1 to the other side, take the square root of both sides, and now you get a plus or minus 1. Let's go ahead and, this is our vertical asymptote. Let's go ahead and draw our vertical asymptotes over here on our graph. And then we get started on our horizontal asymptotes. Now in calculus, one thing you can do is you can take the limit of our function as x approaches infinity. So over here, when the x values are getting bigger and bigger and bigger and bigger, going towards infinity, what is this line trending towards? What is this line right here trending towards? So what you think about is plugging in a really big number for x. You can't really plug in infinity because it's not a number, but you can think about plugging in really big numbers and continuing to do so. And so what does that do? What does that do when you're plugging in really big numbers? Well, what's happening is this denominator is getting extremely big, and so this number as a whole is getting closer and closer to 0. So the y value that we're approaching is 0. So that's going to be our horizontal asymptote. Let's put that on there right there. Now back in algebra, what you guys learned was to look at the degree of the numerator and the degree of the denominator. So the first case was if the numerator's degree was less than the denominator's degree. If this was the case, then you had the horizontal asymptote of y equals 0. Very simple. That's actually my favorite horizontal asymptote just because y equals 0, come on, how can you forget that? The other scenario is when the degree of the numerator equals the degree of the denominator. In this case, what you're going to do is you're going to take the leading coefficient of the numerator and the leading coefficient of the denominator and divide them. Okay? And whatever you get, that is your horizontal asymptote. The last possibility with the degrees is if the numerator's degree is greater than the degree of the denominator. And if that's the case, you don't have a horizontal asymptote. Instead, you have what they call a slant asymptote. You probably don't need to worry about that for what we're doing right now. You're not going to see this probably at all. Now, how do you remember these other two, though? Because those are important. I don't know, maybe you just remember it. If they're equal to each other, then you're going to divide the leading coefficient. And then what about if the numerator is less than the denominator? How do you not get confused with this one and this one down here? Well, I know that I like this one better. Why? Because I like this fraction better than I like this fraction. Why do I like this fraction better? Because he's not improper. The number on top is smaller than the number on the bottom. Same here. The degree on top is smaller than the degree on the bottom. I like him. And because I like him, I know I'm going to get the asymptote that I like. And the asymptote that I like is y equals 0 because he's so nice. Before we get to our first and second derivatives to graph this thing, normally I like to do the Y-Intercept if it's possible. And I'm looking at this really quickly. If I plug in 0 right here, I'm going to have 1 divided by -1. So I get a Y-Intercept of -1. Alright, let's get started on our first derivative. Now for our first derivative, what we have to do is the quotient rule because the denominator is a binomial. So first we take the derivative of the top, which is 0, which is what I have right here. Then you multiply it times the bottom, x squared minus 1. Then we have minus the derivative of the bottom times the top. The bottom gets squared. Let's simplify this guy up. Alright, so we got a negative 2x right here, and then the bottom stays the same. And then we have this setting. We have to set the denominator, or the derivative equal to 0. So we set it equal to 0. We end up getting a negative 2x equals 0, and x equals 0. So x equals 0 is going to be one of our critical points. Let's see, we can do this guy right here. Actually, let's do orange. Alright, at 0, we quite possibly have a change from increasing to decreasing or what have you. So let's pick a number that's before the 0, but still not less than -1, just because I want to stay close. I don't want to pass the asymptote. So I have -1/2. Let's plug in -1/2 to this guy right here and see if we get a positive or a negative. Let's see. -1/2 plugged into the top would be a +1. And then -1/2 plugged into the bottom would be 1/4 -1, and then we have to square it. Alright, we don't have to finish this. We just have to know if it's going to be positive or negative. Now, since we're squaring the bottom, it's always going to be positive. So this side is positive. What about the right side? At the right side, we're gonna pick a positive number between 0 and 1. Let's go ahead and throw positive 1/2 into these x values. Positive 1/2 times -2 is going to be a -1, and in the bottom, again, we're going to have 1/4 -1, and then we're going to square whatever we get. And because we're squaring it, that means the denominator will always be positive. A negative divided by a positive is going to be a negative. So we have increasing before 0, and then decreasing after 0. Alright, let's see what we get with our second derivative. When I take the second derivative, I'm also going to need the quotient rule. So let's see, I'm going to take the derivative of the top, which is -2. I'm going to multiply it times the bottom, which is pretty nasty. Then I'm going to take the derivative of the bottom, which, stinker face, that's going to require the use of chain rule. So we take the chain rule, we get 2 times x squared minus 1. Then we have to multiply that by the derivative of the inside of that, so we have 2x. And then finally we multiply that times the top. Oh man, squeezing everything in here. On the denominator, we have to square that again. So we have x squared minus 1, and then that's going to be raised to the 4th power because we're squaring it again. Now we're supposed to set this thing equal to 0. You're probably looking at this thing and saying, heck no, I don't want to finish that. But before you go too far with that, don't forget, we're multiplying both sides by this, and so it's going to go away, and then we're going to be left with whatever's in the numerator. However, we still have this squared thing right here. This could get pretty dirty pretty quickly. Now this is just a tool. We don't have to use this tool. We could use our other tools and still probably be able to graph a rough sketch of this function. I'm going to go ahead and finish it. Alright, so I can take out an x squared minus 1 from all these guys. So now it's just going to be x squared minus 1 right there, and this one gets canceled out. So what do we have now? We have -2x squared minus plus 2 minus, let's see, that would be 2 times 2x times -2. Negative times negative is going to be positive, so we're going to have 2 times 2, which is 4, times 2 is 8, so we have 8x squared, and that equals 0 now. Remember, the denominator goes away because we multiply both sides by the denominator. It goes away. And so now I have, let's see, 6x squared plus 2, because 8 minus 2 is 6, and now I solve. So let's see, if I move that 2 over, it's going to say -2, and then I have 6x squared. Oh man, this is dirty. That's a -2, not good. Because if I divide both sides by 6, I get x squared equals -2 divided by 6, which we can simplify. However, we have a negative, and we cannot square root a negative. So it looks like we have no inflection points. I'm still kind of skeptical. So let's take a second look at f double prime and simplify this to see if we're missing something. See, we already simplified the top, which was 6x squared plus 2, and in the bottom we have x squared minus 1, and we're going to cube that. Alright, let's think about this really quick. Now, what we want to know is where is f double prime going to be positive and where is it going to be negative? So let's look at the numerator and then the denominator separately. Look at just the numerator. Is there anything that we could plug into that x to make it negative or positive? Actually, everything we plug into there is going to be positive because you're going to square it. If you plug in a -1, it's going to be squared, then you get a +1 times 6 plus 2. So it doesn't matter what you plug into this, the numerator will always be positive. Okay, cool. Well, what about our denominator? Well, it looks like our sign is dependent upon our denominator. So we didn't know where this denominator is going to be positive and where this denominator is going to be negative. So to find that out, let's take our denominator and set them equal to 0. If I set my denominator equal to 0, and then I would, square, or not square root, but cube root both sides to get rid of that nasty cube, I get this, and then I would have to add 1 to both sides. I get this, and then I get x equals plus or minus 1. This is going to take some critical thinking here. When you're thinking about the denominator, and you're wondering where is this denominator positive, where it's negative, you don't really care about this cube. And the reason why you don't care about this cube is pretend this is negative. If I cube it, it stays negative. If pretending this is positive, if I cube it, it stays positive. So I don't care about that cube. So let's look at this right here. Where is this going to be positive? Where is it going to be negative? Well, we just found the x-intercepts for this. If we had a cute little graph, we know that we have an x-intercept at -1 and x-intercept at +1. So what does this graph look like? Does it go like this? Or does it go like this? Because I know it's a parabola. Simple. Let's just find the y-intercept. So to find the y-intercept for this, I plug in 0 right there. What do I get? I get -1. So that means I have a vertex down there, and I have this going on. Now because this curve is below the x-axis between -1 and 1, I'm looking at this -1 and this one, and I'm thinking, alright, if this is negative between -1 and 1, that means we have concave down right here. Between -1 and +1, we're concaving down. So actually, that's what our sine line graph is going to look like with our second derivative. We have a -1 and a 1. We have a negative in the middle, and then we have positives on the left and the right because that's where our line is above the x-axis. Alright, we have our first derivative test and our second derivative test. And I'll be honest, I probably wouldn't do this normally. I would find a different way to do the concavity just because this is dirty. I would need to find out where my lines go without that. Alright, let me clean some stuff up. Now we have something happening in each of these intervals. In the first one, we either have this or we have this. In the second one, we either have this, or we have this, or we have this, or we have this. Now, the more you see these rational expressions, the more you're likely to guess the right one. But I don't like guessing. I like finding the exact answers. Okay, and then in this interval, you either have one of these two curves. All right. So because we did do all that work with the second derivative test, I know that between -1 and 1, we have concave down the whole time. Because we have the first derivative right here, I know that we're increasing then decreasing right around 0. Oh, I didn't put my my first derivative asymptote right there. So there's increasing, decreasing, and we're concaving down. So that part of the graph is done. Yay! Now, what about the left side of -1? Well, we know on the left side of -1 that we're increasing because -1 would be over here, and all this side is positive. Before -1 here, it shows that we're concaving up. So I would have this. Now, if you didn't do the concaving, this sine line, you're probably going to have to pick a point here or here. Now, the nice part about asymptotes is that the lines, the curves that you draw, are attracted to asymptotes. So that means that they're going to get closer and closer to the asymptote as the arrows go out. So you could usually guess the way it's going to look, the way the curve's going to look. All right, now after positive 1, it looks like we're decreasing because that's negative, and then we're also concaving up. So decreasing, concaving up. I wouldn't be able to decrease and concave up in this area, which is why I know it has to be, the curve has to be up there. All right, that's how you do that bad boy. I don't particularly like the second derivative on this one. I probably would do it a different way, but I wanted to show you guys that it can be done.